Chapter 3, Using the Slope to Graph Linear Equations. Section 3.1, Graphing Equations of the Form y equals mx plus b. Alright, we're going to start out with a few definitions from the book, and we're going to define solution, satisfy, and solution set of an equation in two variables. An ordered pair a comma b is the solution of an equation in x and y if the equation becomes a true statement when a is substituted for x and b is substituted for y. We say that a comma b satisfies the equation, and the solution set of an equation is the set of all solutions of the equation. So let's go ahead and test out these definitions a little bit by looking at this example. Which of any of the ordered pairs, negative 2, 3, 0, 8, and 3, negative 7, satisfy the equation y equals negative 5x plus 8? So the way we're going to check these is to substitute them in. These are called ordered pairs, so the first is the x, the second is the y, and we're just going to substitute those in for the x and the y. So the y is 3, and negative 5 times x is what the equation says, and our x would be negative 2, and then plus 8. And what we're wondering is that true or not? Because if it's true, then we've got a solution right there. So let's see, I have 3, and then negative 5 times negative 2 is positive 10, and then the plus 8. So that looks like 3 equals 18, which I'm not a believer in that one, so I'm going to cross that off, and I'm going to say no to that one. That one didn't work. I tried to substitute those values in for x and y. When I did that, I did not get a true equation. So let's test this next one, where the x would be 0 and the y would be 8. So we're going to plug that 8 in for the y. And then negative 5 times 0 plus 8. So that would be 8 equals 0 plus 8 when I multiply those two. And that looks like it does work. So this one looks like it is a solution. And let's go ahead and check the last one as well. It is possible for a linear equation to have more than one solution. In fact, we'll find out they usually have infinitely many. So the y value is negative 7, so I'm going to substitute that in on the left. Equals negative 5 times the x value, which is 3. And then add the 8 and then see is that true or not, just like we were checking on that one. So on the left we have negative 7. Multiplying this through we get negative 15. And then plus 8, and negative 15 plus 8 is negative 7, so that one does check. So there's another solution. So which, if any of the ordered pairs satisfied that equation? It looks like 0, 8, and 3, negative 7 get the job done. So there's my answer to that question. When you do this in my math lab, you'll want to put one ordered pair, and then I believe they'll ask for you to put a comma and then the second ordered pair. To list those when you have more than one ordered pair that works. Let's go ahead and look at another definition, which is graph. The graph of an equation in two variables is the set of points that correspond to all the solutions of the equation. So you see on this example up here that it's possible to have more than one ordered pair that works. And as we did work through this, I mentioned that there's usually infinitely many. So there's no way we could ever list all the solutions if there's infinitely many, but we could draw a picture of it by connecting them all with a smooth curve. And it turns out that the graph of any solution set to y equals mx plus b turns out to be a line. So the graph of an equation in the form y equals mx plus b, where m and b are constants, always turns out to be a line. Alright, so let's go ahead and see how we would do a graph of such an equation then. So let's try and find the intercept of this and then graph and then verify with the graphing calculator. So when we go to find the y-intercept, that's the place where it crosses the y-axis. And the easiest way to find that is to make a little table like this where we're going to list ordered pairs that solve this equation. And we know that the intercept, the y-intercept, comes when x is 0, so I'm going to put that into the table, but I want to know what y goes with it, so I'm just going to plug that x of 0 in. So y equals negative 3 times 0 plus 5, and that's 0 plus 5, which is just 5. So apparently the y that goes with an x of 0 is 5, and so this would be my y-intercept right here. And that's one solution to the equation. Now if I know that I'm dealing with the equation of a line, then if I get just two ordered pairs, I could connect those and that would draw the line for me. Usually we do 3 just to play it safe, and when you have y by itself in your equation, the easiest way to get more is just to pick some x's and plug them into the equation. So I'll pick something positive and something negative. So if I put 2 into this equation, I get y equals negative 3 times 2 plus 5. That would be negative 6 plus 5, or negative 1. So if I put 2 in for x, I get negative 1 out for y. And then let's do one more just as a check. We'll plug that negative 3 in for the x and see what we get out. So the two negatives multiplied together there make a positive and positive 9. And then I still have the 5, and I add those together and I get 14. So I have 3 ordered pairs now that I can plot and connect with a straight line to draw the graph. So there they are, that first one being the y-intercept. Alright, so I do want to graph this, and to do that I'm going to have to think about scale. Since I have that number 14, I'm going to have to decide how to fit that in. And let's go ahead and let's see, that y value of 14 is big, and I have a negative 1 as my smallest y. So I don't have much to plot below the x-axis, but I have to go pretty high above. So I'm going to draw my horizontal axis, the x-axis, down kind of low to give room for big y values like 14 and not worry so much about space below because I don't have big negative y's. I picked the x's and I picked some things on both sides, so I can just pretty much draw my vertical axis down the middle and everything should fit nicely with a scale of 1. And I know that because I picked the x's and I picked numbers that would be easy to plot, like 0, 2, and negative 3. Alright, so now that I go to graph this, I need to think about what scale to fit 14. And I have 1, 2, 3, 4, 5, 6, 7, 8 squares there, and I need to make it up to 14. So if I take that 14 and divide that over 8 squares, that would be 1.75. So I think if I number in 2's, I'll be able to plot that 14. So let's see, 2, 4, 6, 8, 10, 12, 14, 16. So that 14 is going to fit, and I have to be consistent with that scale. So this would be negative 2, 4, 6 in this direction. So when I go to the x-axis, I can pick a different scale. It's okay if the x and the y are different from each other, and since these numbers are small, I'm going to go ahead and just number in 1. So 1, 2, 3, 4, 5, and negative 1, 2, 3, 4, and 5. And then go ahead and plot the points that we have. So over 0 and up 5. Remember we numbered in 2, so this is 2, 4, 6. So 5 is right in between the 4 and the 5, or the 4 and the 6 notch. And then over 2 and down 1. We'll go over to 2 on the x. I have to remember that I numbered in 2's on the vertical, so down 1 is actually just down half a square. And then left 3 and up to 14. And 14 is one notch above the 12 since I numbered in 2's. And what we're looking for with our 3 points is that they would line up, and it does appear that that is happening. Once they line up, I can go ahead and throw my ruler in there and connect those with a straight line. So one of the questions I like to ask when I'm in class with folks is, how many solutions did we just graph? And a very common answer that people will give is they'll say we graphed 3. And that was true until we drew the line. Once we drew the line, we actually switched to infinitely many solutions. Remember that what a graph represents, if I go back up here, the graph of an equation in 2 variables is the set of all the points that correspond to solutions. So not just those 3 that we found, but this line is representing the infinitely many more that we didn't work out but still solve the equation. Alright, they asked me to verify this on the graphing calculator, and so I'm going to do a little scratch work on paper before I go to the graphing calculator to help me set up my window. I want the window to look basically just like this grid, so I'm going to think about what is the x min and the x max. So the x min on this looks like it would be 4, 5, negative 6. And the x max, 1, 2, 3, 4, and 5. And then just some other notes here. So the y min and the y max would be good to know as well. And for the y minimum, we want 2, 4, negative 6. And on the y maximum, 2, 4, 6, 8, 10, 12, 14, 16 would be our y max. So I want to have all those settings match up so that I get a picture that looks a lot like this one. Alright, so let me go ahead and bring the calculator in. And we want to go ahead and enter in our equation. So the way you do that is you go to the y equals menu right here, and you just want to enter y equals the equation they gave us. So let me slide that out of the way. Negative 3x plus 5. So negative 3 times x plus 5. It's worth reminding you here, I think, when you put a negative in like that, make sure you're using the negative key when that's the first sign that you're typing. If it was a subtraction, that would be fine. Like if this was a minus 5, I'd use the subtraction key, but when the first thing is a negative, make sure you're using the negative key. So I've entered in my equation, and I could graph that, but if I do, who knows if I'll even see it. Yeah, my window isn't set up right to see that graph. So what I want to do is make sure the window is right. So the window button is right here, and I want my x min to be negative 6. Again, make sure you use the negative key and not a subtract key. And the x max is 5. And the scale, we went 1, 2, 3, 4, so we were numbering in ones there. And for the y minimum, negative 6. For the y maximum, 16. And for our scale, we went 2, 4, 6, 8, 10, so we were numbering in 2s. So now if I hit graph, I should see a graph that looks a lot like this. Maybe not purple, but basically the same picture. And that does indeed look like it matches up pretty well, so that's good confirmation that when we did the graph by hand, we did it correctly. Alright, moving on to page 2, let's go ahead and try another one of these graphs, both by hand and on the graphing calculator to check our work. So when they have the y equals like this, as I said on the previous page, I think it's a good idea to start out by just picking some x's over here. And let's see, I'll do the 0 to get the y-intercept. So what goes with 0? Let's see, y equals 1/3 times 0 minus 2. All that just cancels out. So I get y equals negative 2. So 0, negative 2 is my y-intercept. And now I want to plug some x's in like I did before, but this time I'm going to be a little bit more careful about the x's I pick. If your x is being multiplied by a fraction and you want to avoid fractions in your work, then you should pick a value of x that's a multiple of that denominator. So for example, picking something like maybe 6 and maybe something like negative 3. Those are both multiples of 3, so when I plug them in, they'll cancel with that, and I won't end up with fractions in my y value. So let me show you the work on the 6. That'd be 1/3 times 6 minus 2. And here the 3 goes into the 6 twice, so it looks like I'm going to end up with 2 minus 2, which is 0. So 6, 0 is another point on the graph. And then doing the last one, y equals 1/3 times negative 3 minus 2. So this time the 3's cancel, but there'd still be a negative 1 left there. So negative 1 times negative 1 would be negative 1, and then minus 2, and they're both negative, so I would add them together and get negative 3. So now I have 3 ordered pairs, 0, negative 2, 6, 0, and negative 3, 3, and I just want to go ahead and graph those. And all these numbers are fairly small, so as long as I'm thoughtful about where I set my axes, I should be able to graph them all. The biggest number is 6, and that's an x value. So I'm just going to make sure that I draw my y-axis here a little bit to the left. That gives me more room on the right for positive x values than I have for negative ones, and that's good because I have bigger positive x's than I do negative ones. None of my y values are very big, so I'll just go with a horizontal line kind of near the middle. And then go ahead and plot our ordered pairs on there. Actually, we've got to set up our scale first, but we did our positioning here so that we could number in ones. But even when you're numbering in ones, you do need to indicate to people what that scale is that you decided to use by making some tick marks and numbering at least a few of them so that people can see your choice of scale. And then start plugging in those ordered pairs onto the graph: over 0, down 2, over 6, up 0, and then hopefully the third one will line up: left 3 and down 3. And does it line up? Yes, it does. Bring in our ruler then and connect those with a straight line. Alright, so then the only thing left to do would be to check that on the graphing calculator. So I'm going to go ahead and just do everything kind of on the fly here without the scratch work this time. So I'll want to enter in the equation. So y equals, there's our old one, so I'll just hit clear. And then what's our new one? 1/3 times x. So 1/3 you just enter using the division key. And then times x, and then minus 2. So if I hit graph on that right away, I'll get some graph. It doesn't quite look like this because I haven't done anything with the window. It's kind of close, but if I really want it to match up, I want to make my window look like this grid. So let me go into the window settings. My x minimum looks like -4, and the x max, the last thing I numbered was 6, but I still have one more square, so that'd be 7. And I did number in ones. And for my y minimum, it looks like down to 5 and up to 6, and also numbered in ones on there too. So if I hit graph again, I'll get something that looks a lot more like my hand-drawn picture on the screen. Alright, so it looks like that's checking out okay. Alright, so moving on, the y-intercept of the graph of y equals mx plus b. The graph of an equation of the form y equals mx plus b always has a y-intercept 0b. So both times when they want us to find the y-intercept, I did that by plugging in 0, and this is just a reminder of that right here, that every time you do a y-intercept, this is always going to be a 0 for the x-coordinate, and then you plug in that 0 into the equation to figure out what the b is going to be. And then here's just kind of step by step on what we did when we went through and we graphed our equations. So pick any value for x and plug that into the equation. Now it turns out if you'd prefer, you could also pick a value for y instead, but if they've got y by itself, you're going to find it much easier to pick an x. And then if you picked an x, you would then solve for y by doing the math and working out what y is equal to. If you had happened to plug in a y, then you would do your solving for x, and we'll see some of that happen later on in the course. And once you've plugged in your x and you solve for your y, then x comma y, the ordered pair, is the solution. Alright, let's go ahead and try and grasp some of the concepts with graphing here by looking at one more example. The graphs of equations 1 and 2 are shown in the sketch below. So they're saying this one's equation 1 and this one is the graph of equation 2. Which ordered pairs satisfy equation 1? Now they haven't listed any ordered pairs in the sense of an x comma y, but each one of these points represents an ordered pair, so they just want us to reference the letter. So what we need to remember here is that a graph of equation 1 is the set of all the solutions to equation 1, so everything that is on equation 1 or on the graph of equation 1 satisfies equation 1, and all the stuff that's not on that line does not satisfy 1. So which ones are on equation 1? It looks like A and E. So to satisfy the equation, it has to be on the line. So the only points of all these they listed for us that are on equation 1 is A and E. And then which ordered pairs satisfy equation 2? So now we have to be on the graph for equation 2. It looks like that would be E comma F. Which satisfy both? Well, you can see the E that is in common. When they ask that, what you'll always get for that answer will be the point of intersection, and that'll be important for us to remember later on in the course. But the point of intersection is always the one that satisfies both. And then which of the points satisfy neither? Well, that would be any points that aren't on either of the lines. So B, C, and D will all go into that category of not solving either of the lines because they're not on either of the graphs. So what we're trying to cement in there with an example like this is that idea that every point on a graph is a solution to the equation. So when we draw in this line, we're not just showing two solutions A and E, we're showing infinitely many. Everything on there is a solution, and I know B is not a solution because it's not on the line. So every point on a graph is a solution and satisfies the equation. Every point that's not on that line is not a solution and will not satisfy the equation. Alright, moving on to page 3, we're going to do something here that you might not find really comfortable initially because we don't have a procedure for it yet, so we're just trying to kind of wing it. But they want us to find an equation of a line given some ordered pairs. And the first one I think actually starts off pretty easy, but what we want to figure out is an equation of the type y equals mx plus b. And so we want to figure out what is the m and the b to make that work. Well, one of the things that we want to remember is that if you put in an x, then what you get out is the y-intercept value b. Remember, the y-intercept is always 0, b. So if they show you a table and the x is 0, then whatever goes with that is always the b. So I'm learning from this table right away that b is equal to 0. So I could move down then and say, okay, so my equation is y equals mx plus 0, or just y equals mx. So now really what I have to figure out is what's the multiplier. So this is a little tricky because the chart's the same, but what do you multiply 3 by to get 3? What do you multiply 4 by to get 4? If you think about it, since it's not changing, the answer must be 1. So I think that because these are just a matchup, that we're going to have m equals 1, and our equation will just be y equals 1x, or just y equals x. And I'm going to box that, but let's just test it. If x is 3, you plug it in. What's y? It's also 3. I think this makes sense. Every x and every y are the same, and so we come up with an equation that says y equals x, or that y is always the same as what x is. I think that one's almost kind of tricky because it's so easy with the numbers matching. Let's try another one that's actually a little bit messier, and I think we'll get the pattern a little bit better in this. So the graph of an equation is shown below. Create a table of ordered pair solutions of this equation, and your table should contain at least 5 ordered pairs. So I want to make a table where I put x's and y's together. And I'm going to do that by just trying to find nice points on this graph. So here's one, and it looks like this is one, and this is one. Probably that's one. This is one, this is one. Now, I could put my pen anywhere on the line and say, here's a solution. The ones I'm picking because they're right on the intersection of these grid lines. And if they're on grid lines, it means that not only are they solutions, but they're solutions with nice ordered pairs. They said at least 5. Let's do all 7 that we listed here. So what's the first one? Well, what's its x value? Looks like the x is -3. And what's the y value? This is 2, 4, 6. So -3, 6 is one of the ordered pairs. So what's this one? Left 2, up 4. And then it looks like we've got left 1, up 2. And then right at the origin there, so a 0 and a 0 together. Here we have over 1, down 2. And then when we go over 2, we're down 4. And then the 7th one over here, if we go over 3, it looks like we're down 6. So now the question is, what's the equation of the line? Well, because it's a line, it's going to have an equation of the form y equals mx plus b. And they're being kind of nice to us so far. They keep giving us y-intercepts that have a 0, and that does make this process a little easier. When that's not a 0, we'll have to work a little harder. We'll see that in later sections. But if the x is 0, whatever goes with it is b, and so it's 0, 0, so that tells us that b is equal to 0. And so I can write my equation from that as y equals mx. And then it's just a matter of figuring out the multiplier. So what are we multiplying these by to get these numbers? And this is just something that's either going to probably strike you or it's not. But it looks to me like these are all double. So like if you double 3, you get 6. If you double 2, you get 4. If you double 1, you get 2, and so on. So my temptation is to put y equals 2x, but notice that doesn't quite work because there's a sign difference. So I need to take my x, make it twice as big, and change its sign. And I believe the multiplier that will do that would be a -2. So here's my theory that this is the equation. And I'm just going to test that on a couple of the points. If it works for 2 of them, it'll work for all of them. Let's try that for 2, -4 and see if it works. So what is y if I plug in a -2? And sorry, I guess I'm testing that point right there. So I put in an x of -2. So what do I get there? -2 times -2 is +4, so that does check for that one. Let's try this one down here. Plug in a 3. If we plug in a 3, we get -2 times 3, which is -6. So for both of those I tested, when I plugged in the x, I got out the y. And if it works for 2 points, it's going to work for all of them. So we'll find a more official procedure for finding the equations of those lines later on. But right now, do the best you can with this, just to do it by intuition, by struggling, by fighting through it. And we'll have a better method later on, but if you've been able to struggle with it and figure them out, then it'll be easier to do that official method later on. Alright, that wraps up section 3.1.